Hey everyone, and welcome. Today we're going to be exploring one of the coolest, most dynamic shapes in all of mathematics, the hyperbola. Now, it might look like an ellipse's weird cousin, but it has this incredible power, and it all comes from one tiny, tiny change in an equation you probably already know. Let's get into it.
So let me ask you something right off the bat. What on earth could possibly connect the sweeping, majestic path of a comet flying through our solar system with a ship trying to figure out its exact position in the middle of a huge ocean? Well, the answer, believe it or not, is the hyperbola. And today, we're going to see exactly how.
At first glance, these two equations look almost the same, right? You're definitely familiar with the ellipse, that perfect closed loop. But look closer. See that? The only difference, the only thing that separates them, is that one little minus sign. That single change from a plus to a minus literally blows the shape wide open. And that's the secret we're going to unlock. All right, so let's jump right in and decode its fundamental structure. We're going to break it down piece by piece so you can see exactly how this thing works. No mysteries here, I promise. Okay, so this is your standard bread and butter horizontal hyperbola. It opens out to the left and to the right, kind of like two parabolas that are facing away from each other. And here's the dead giveaway. The x squared term is the positive one. That's what tells you it's opening horizontally along the x-axis. Okay, every hyperbola has a main axis. It's called the transverse axis, which sounds a little fancy, but really it's just the line that cuts right through the middle and connects the two curves. Its length is always 2a, and it tells you the distance between the two most important points of the hyperbola.
So what are those important points? We call them the vertices. Think of them as the turning points for each of those curves. They're the spots that are closest to the very center. For a horizontal hyperbola like this one, you'll find them at positive a0 and negative a0, 0. And that a comes straight from the equation.
Okay, listen up, because this is a huge deal, and it's probably the exact opposite of what you remember from ellipses. With a hyperbola, you add, I'm going to say it again, you add a squared and b squared to find your c squared. This is where so many people trip up. So let's just burn this into our brains right now. Hyperbolas, you add.
Okay, enough theory. We've got the formulas, we've got the concepts. Let's actually put this stuff to work with a real example. We're going to take all those pieces and map out a hyperbola from scratch.
All right, here we go. We're given the equation x squared over 16 minus y squared over 9 equals 1. Our job is to pull this equation apart and find all its key components. Let's get to it. All right, let's break this down step by step. First up, we need our a and b. Easy enough. A squared is 16, so a is just 4. B squared is 9, so b is 3. Done. Next, let's find c. And what did we say about hyperbolas? We add. So c is going to be the square root of 16 plus 9, which is the square root of 25. So c is 5. Boom. Now we have everything we need for our key points. The vertices, they're at plus or minus a, so plus or minus 4 is 0. The foci, they're at plus or minus c, so plus or minus 5, 0. Last but not least, those asymptotes, the invisible guidelines for our curves. The formula is y equals plus or minus b over a times x. So for us, that's y equals plus or minus 3 over 4 times x. And just like that, we've sketched out the entire hyperbola without even drawing it. Pretty cool, right? Awesome. But, life isn't always that neat and tidy. What happens if the hyperbola is flipped on its side or shifted off the center? Well, the good news is the rules don't really change. It's all the same logic, just with a couple of minor tweaks. Okay, check out this equation. See what's different? Right away, you should spot it. The y squared term is positive this time. That's the signal. That tells us this thing opens up and down, vertically. The rules are the same, though. A squared is under the positive term, so that's 25, meaning a is 5. B squared is 4, so b is 2. And that means our vertices are now on the y-axis at 0, plus or minus 5. Oh, and the slope of our asymptotes? It just flips to a over b. It's all the same logic, just, turned 90 degrees. So what about shifting the whole thing off the origin? It's exactly what you'd expect. First things first, find the center. Look at the x plus 1 and the y minus 2. That tells us our new center, our h comma k, is at negative 1, 2. And from that point on, everything is based on that new center. Our a is 3, right? So we just count 3 units left and right from the center to find our vertices. The asymptotes, they run right through that new center too. It's the exact same shape, we've just picked it up and moved it. Okay, before we get to the really cool real-world stuff, let's talk about a few common mistakes. Seriously, getting these little details right will save you so much frustration, so let's make sure we nail these.
Here it is again. I'm showing you this side by side because I cannot say this enough. For hyperbolas, the foci are outside the vertices, so c has to be bigger than a. It just makes sense that you add. C squared equals a squared plus b squared. For ellipses, the foci are inside, so you subtract. Just remember, hyperbola, add. Got it?
All right, here's another huge one. Remember how with ellipses, a was always the bigger denominator? Forget that. Throw it out the window. For a hyperbola, a squared is always under the positive term. I don't care if it's bigger or smaller than b squared. If it's under the positive term, it's a squared, period. And finally, let's clear up any confusion about the asymptote slope. Just think about it as rise over run, and it makes perfect sense. For horizontal hyperbola, you rise by b and run by a to make that little box that guides the curves. So the slope is b over a. For a vertical one, you rise by a and run by b, so the slope is a over b. See? It's just about which way the box is oriented.
All right. We have cracked the equations, we've dodged the common mistakes. Now, for the fun part, the payoff. Why should you care about any of this outside of, passing a test? Well, let's look at one of the most brilliant real-world applications of the hyperbola.
So, this system is called LORAN. It stands for Long Range Navigation. Picture this. You're on a ship out in the middle of the ocean. There are 2 radio towers on the coast, and they both send out a signal at the exact same instant. Naturally, because you're not in the dead center, you'll get one signal just a fraction of a second before the other. And here's the magic. The set of every single possible point where you could be that has that exact same time delay, it forms a perfect hyperbola. So you know your ship is somewhere on that giant invisible curve. So what do? You listen to a second pair of towers. You get a different time delay, which gives you a second hyperbola. And where those 2 hyperbolas intersect, that is your precise location. It's absolutely genius.
And that really is the whole story. We started with a single minus sign. That's it. And we watched it completely blow up a nice, neat ellipse into this wild, 2-branched shape that can map the path of a comet or guide a ship safely home. So it kind of makes you wonder, right? If one tiny sign change can unlock a whole new universe of shapes and uses, what other incredible secrets are just hiding in plain sight in the math we think we already know?